Thank you for coming, everybody. Indeed, I will be talking about constrained Willmore surfaces in R3 and R4. So to begin with, let's say, what is this Willmore business? And so we need the Willmore energy. I think it's easiest if you just imagine in your head R3, very classical differential geometry. You have the Gauss curvature, you have the mean curvature of some surface in R3. And very famously, the Gauss-Bonnet theorem is if you integrate up all the Gauss curvature, you get this relationship with the Euler number of the surface. Right? And so the question that was posed by Willmore is, what happens if you integrate up all the mean curvature? And we know that mean curvature can be positive or negative and change across the surface. So take the square so that you have an interesting quantity. What's the geometric meaning of this, though? Well, we know if you take the difference of the principal curvature squared and expand that out, and if I can expand this out correctly, or if I rewrite this, you can rewrite this then as the sum squared and then a correction, whatever, 4 times the difference, right? You do this trick to change minus 2k1, k2 into plus 2k2. So the difference between h squared and this is exactly a product k1, k2, namely the Gauss curvature. So that gives you this term here. And so we see up to some constant that just depends on the topology of the surface, the Willmore energy, the square of the mean curvature, is measuring how far you are from being a sphere. So a sphere or a plane has equal principal curvatures. And so this is, in some sense, measuring how far you are from being a sphere or a plane. Yeah, and so a Willmore surface then is a critical point of this energy functional. I'll just now start calling it energy. In nature, this is related to certain membranes and how they stretch. That has this sort of physical interpretation as well. But for us, as mathematicians, what's most interesting is that this is a conformal invariant. So this is maybe clear under the Euclidean motions. So obviously rotations and translations don't change the mean curvature. If you rescale the surface, you just rescale the mean curvature, but you rescale the area in the opposite way. All right, so then these cancel out and it's it. So maybe what the remarkable thing is that if you do some Mobius inversion, so an inversion of the sphere, this also stays the same. And this is kind of a bit remarkable. So it turns out that this is the Willmore energy is a conformal invariant. And so for this reason, it's a very natural problem. Sorry for the frequent coughing breaks that are going to happen. To fix a conformal class of a surface. So not just take, say, a torus, but to fix a conformal class on the torus. I see there are some students here. Should I give some more explanation for what that is? That's okay. And so then a constrained Willmore surface is, instead of looking among all immersions of the surface, which one is a critical point for the Willmore energy, you only look among conformal immersions of the particular class that you've chosen. And this gives you a constrained Willmore surface, so a bigger class. Do we know, sometimes people give definitions and the question is, well, are there actually any of the thing that you defined? And constrained Willmore surfaces and Willmore surfaces are actually some large class of surfaces. So all minimal surfaces are Willmore surfaces, for example. But there are Willmore surfaces that are not minimal surfaces. So for example, Hoftori, these were constructed by Pinkel. You take some elastic curve on the sphere, on the 2-sphere, and then you take the inverse image of this under the Hopf vibration of S3 over S2. Right, and then this gives you a tube in S3. And these are examples of Willmore surfaces that are not minimal surfaces, for example. So there are others there as well. And I came into this field studying constant mean curvature and harmonic surfaces. So constant mean curvature here. All constant mean curvature surfaces are also constrained Willmore surfaces. So this is a bigger class than constant mean curvature. And hopefully at the end, I'll come around and try to put them into a hierarchy with each other. Yeah, so here on the right, we have the very famous example of the Venter torus, which is a CMC surface, three-word CMC surface. Yeah. So what is actually known about these things? So Willmore's initial paper where he made this suggestion was very brief, and he only checked tori revolution, and he found that, he just varied the two different radii, and he found, there's a minimum here among these for the Willmore energy. Maybe that's the minimum for everything. And so he conjectured that the Willmore energy was greater or equal to 2 pi squared. That's when one radius is 1 and the other is the square root of 2. It turns out that that is the stereographic projection of the Clifford torus in S3. So the Clifford torus in S3 is some minimal surface in S3. And if you take the stereographic projection to R3, then you get exactly this guy. Then there were other works, the theory developed, and there's this result by Li and Yao that if you have non-injectivity, so the surface is crossing each other, right, then that forces you to have some amount of Willmore energy. Right, in order to bend around and meet yourself, you need to have a certain level of Willmore energy, and the more points that are bending around and meeting themselves, the more Willmore energy is forced. So all the time when you read results in this field, there'll be like some result for less than 8 pi, or some result for less than 12 pi, and it usually comes back to this very useful result about what you can exclude by having multiple points. Next, it was understood for spheres, how to do this for spheres. And this is maybe the most relevant for us because Bryant reduced this to a problem in algebraic geometry. All right, he connected this to minimal surfaces, and then you have some holomorphic differentials. And with this, then you get started going with algebraic geometry, and everything is quite, not finite, but sort of finite degree, and you can get some good classification. And it turns out that all Willmore spheres have energy multiple of 4 pi, with the round sphere itself having Willmore energy 4 pi. Right, you can go back to the slide several pages ago. The round sphere, the principal curvatures are equal to each other, so that term was 0, and you just have this 2 pi Euler number term. Okay, and then we get into results which are more of the direction that I've been working on, the existence of tori minimizing the Willmore energy was proved by Simon. This Willmore conjecture that this particular is the minimum on tori, this was proved. And several papers by different combinations of these authors succeeded in proving the existence of constrained Willmore surfaces in every conformal class and in different numbers of dimensions. So my work, which I should say is with Martin Schmidt, has been to try to build a theory about this that makes it make sense, right? To see why these techniques actually work and to develop more powerful tools to get this result. Okay. And so what's our idea for making this simpler? As I said, the Bryant work is really good because it reduces it to holomorphic functions, holomorphicity, and algebraic geometry. So can we do something like that? Well, let's think about how you can take a Riemann surface. We're going to fix the conformal class, so we have a Riemann surface. And how can you put it into some other space? Well, if you have a map into CPN, you can write this function in homogeneous coordinates, where each of these is a meromorphic function, right? A holomorphic map into CPN. My favorite example of this is the embedding of the torus into CP2, because you have these very classical functions that you're forced to learn. Okay, one, maybe you learned this already in primary school. But then the Weierstrass P function, which I don't know, you maybe learn in year 8, and then its derivative. And if you take the 3 of them as your coordinate functions, this is, it gives you, because the derivative and the function satisfy some algebraic equation amongst yourself, you get this image, algebraic curve image of the torus in CP2. So this is a really nice example, and because this is a holomorphic map, it's a conformal map in particular. And so this is an example of a conformal immersion of a torus into CP2. Now these are mirromorphic functions, but instead we can consider them as holomorphic sections of some line bundle. So everywhere they have a root, you add a root to the line bundle to get rid of this. And the note is that changing by a cocycle, that is multiplying by a holomorphic function, doesn't affect the embedding at all. All right, so here, in the neighborhood of z equals 0, the third order pole is now cancelled out by the z3, and you have some well-defined function. Right, so if you're looking at this sort of setup, then holomorphic sections of line bundles is the way to go. I should say we call this the Kodaira map because there's a Kodaira embedding theorem about putting curves into CPN, and we didn't have a good name for this sort of thing. So. So now we start coming to why R3 and R4. And the answer is because R4 is the quaternions. Obviously. And what makes the quaternions nice is that they describe their own rotations. Right? The multiplication in the quaternions describes rotations on the quaternions in just the same way as multiplication in the complex numbers describes rotations in the complex numbers. And this makes working in geometry, the geometry in the quaternions, absolutely nice. So in particular, we want to describe the condition that you have a map into the quaternions and that this is a conformal map. So on the left-hand side here, we have the Hodge star. This describes a 90-degree turn on the surface before it's immersed. And then on the right-hand side, we multiply the immersion by a 90-degree turn described by a quaternion. And you have a conformal map if these agree with each other. So this is our definition of conformal into the quaternions. All right, there's some weird issue that is probably not important, but there are different sign conventions for the Hodge star. So the fact there's a minus sign here is just this annoying conventions at work. This is the correct. And that n is a unit length, purely imaginary quaternion means that it encodes a 90-degree rotation. All right, so what is going to be our strategy? Our strategy is going to try to take this and make a weak version of the problem. All right, because we want to look at minimizers, and a very standard strategy if you want to find a minimizer is you formulate a weak version of the problem, then you prove that limits have some, if you take some sequence that there's some weak limit, and then if the weak limit is special in some way, such as that it's a minimizer or a critical point, then typically you have better regularity, and then you improve the regularity of the limit. This is the standard PDE solution strategy. And this is a strategy we want to employ to prove stuff about constrained Willmore surfaces. So how are we going to weaken the problem? Well, we should allow F to be a W11. This is basically the weakest thing you could possibly allow and still have dF make any sense. Right? dF has to be a one function. Because you want to have some notion of the two tangent planes turning, right, it needs to be almost everywhere rank 2, so you have some notion of tangent plane. And what do you need for the n? Well, we need W12 to make the theory work. But that's also, if you look inside the theory, a very natural condition. So that's our weak version of the problem. And so An admissible map has this regularity and this equation holds, right? So it's weakly conformal. This equation holds in the sense of measurable functions, and you have this level of regularity.
Does the regularity of F not already imply a regularity on N and vice versa with that through the equation?
Yes, and this is stronger.
This is stronger. So does it, but then does it not imply already a higher regularity than on F if you have this equation?
Yes, but it's not exactly clear how.
Okay.
Yeah. I think in the end it implies that F, like after you go through everything, it implies that F is actually W22. Yeah, which again would fit, because if F is W22, then DF is W12, which then fits exactly with N. Okay, so what did the last two slides have to do with each other? We had, on one hand, this idea of the Kodaira map of holomorphic embeddings, and on the other hand, we had this definition of conformal immersion. Well, a function is holomorphic. One way to write that condition is that, writing it with D star, is that D minus I star D applied to F is 0. Right? And if you expand out what this is, you get exactly this dz bar operator, which is, of course, implies holomorphic. The similarity is if you take that conformal, the equation to be conformal, and rearrange it in the same form, you get this condition here. And these look suspiciously like each other. The difference is that the complex I, which is a 90-degree rotation, has now been replaced by a quaternion rotation of 90 degrees. So in this sense, this is a generalization of the usual holomorphic condition. Now there's some very quick procession of introduction of terminology to get the setting right. Feel free to ask more questions if you want, but it's not essential for the rest of the talk, so I might go through it pretty quickly. You're mapping into the quaternions, so you have this trivial quaternionic bundle on the surface. You can use N as a complex structure on this bundle to split this bundle into pieces. One of those pieces is itself a complex vector bundle, and the trivial connection on the quaternionic bundle then descends to a holomorphic connection on this complex vector bundle. Basically, giving you this guy down here. And yeah, so what you get is a holomorphic line bundle and this N. And so we have what we call the Kodaira representation on a Riemann surface, and you have an admissible map. We associate to this a quadruple of data. So on one hand, we have this holomorphic line bundle E that I just explained extremely briefly. We have an L2 potential V. So this is an endomorphism of the quaternionic bundle. And these two go together to give some sort of derivative. And then additionally, we have two linearly independent sections of this bundle. And they're V holomorphic. Okay, I said I wasn't going to use the board, but can I cheat? V holomorphic means that D bar coming from the holomorphic line bundle E minus this potential when acting on a section gives 0. Right, so regular holomorphic would be V equals 0, and so we have some extension of the notion of holomorphic, which we call V holomorphic. So I've somewhat explained, and the relation to the admissible map is that F is the quotient of these two sections. Or if you think of this into projective space with two coordinates, then you have upsilon and phi as your two coordinates. And then when you want to put this back into affine space, you would take the quotient. And so this is much like the Kodaira, the normal Kodaira embedding, except you have this notion of V holomorphic instead of the usual notion of holomorphic. You have V holomorphic sections whose quotients give the map. So this is our setup. And so instead of working with admissible maps, we all the time work with this line bundle and this potential in these sections. So that was a lot to throw at you. Are there questions at this point? No? Is the clock in the back accurate? Maybe that's also useful to know? Okay, good. So it's one thing to give definitions. You should also give some example. And what could be the simplest interesting example? Okay, I can give you planes, I can give you spheres, but let's try to do something that's a bit different. So let's take the Riemann surface to be, well, it's going to be a sphere, but let's make the potential interesting. So we make the potential interesting by being 0 outside the disk and by being a non-zero constant inside the disk. Yeah, for reasons that maybe we get into, it should be j times some real constant, right? Potentials which are valued in jk are special in our theory. Okay, so if you have such a potential, what do the V holomorphic sections look like? Well, on the part where the potential is 0, they should of course just be holomorphic sections in the usual sense. But on the part where it's non-zero, then you can write down the equation and break it into parts, and what pops out is Bessel's equation, which is nice because there's a big table on the internet where you can look up all the properties and you don't have to do it yourself, in particular Taylor expansions and whatnot. And so that means that I can make a demo out of it. So if I get this correct. So what I have here, okay, maybe I said I wasn't going to do the sphere, but this is clearly a sphere, well, half of a sphere. I've cut the top off. But on the other hand, this is very hard to see, I've made V equals 0 in this picture. So the green half is the outside of the disk, the image of the outside of the disk, and the orange half is the image of the inside of the disk. So what happens if I, oh, this is actually going to be hard to control. Sorry, what happens if I increase the potential? Well, what's happening is it's starting to bend. Like so, and eventually it bends so much that it pops around and you get something like this. And the more you increase V, the more spirally and spirally and spirally it gets, basically. But I don't know, maybe if you get your ruler and protractor out and you drew some curvature lines and held them up, you'll see that this is a conformal immersion of the sphere into the space, with this slightly weird thing that here it goes from being part of a round sphere to being more curvy, right? Which is sort of outside the bounds of usual representation by smooth functions, right? It's not smooth at this point. Okay, let's go back to the thing. Now everything I explained was in the quaternions, but this talk has R4 and R3. So how do you get to the R3 part? Well, you need a slightly different representation to make that work, right? Because it's very hard to control when the quotient of something is going to be imaginary quaternion. So R3 we control as being the imaginary quaternions. And the trick to controlling them is to have this other representation. So I threw up a calculation here. I'm not really expecting anyone to go through it. But we started with f is the quotient of of upsilon and phi. And if you apply the normal rules for differentiating a quotient when you have a non-commuting algebra, so don't put a squared minus 2, right? You have to make sure that the inverses are on each side. Then this is just the quotient rule. And we factor the upsilon and the d. Oh, actually, we just factored the upsilon in the first step. And we have the d phi, and we have this d upsilon. Now, because both phi and upsilon are v holomorphic, the d bar parts of their derivative are essentially v times themselves. So if you look at the dz bar part of the derivative here, you'll get dz bar v phi, and here you'll get dz bar v upsilon times upsilon inverse times phi. So you'll get v phi. And so the dz bar part of this cancels out, and you just get the d part. And then you do some trick here, which is well justified in the big theory, but not important for this talk. And what you get is you get two new holomorphic sections. This one, there's some new potential u, and the section on the right here is u holomorphic, and this crazy combination here, this is k u bar k holomorphic. So unlike for the Kodaira representation where they were both v holomorphic with the same v, here you have two holomorphic sections, but the potentials are different. Different but related. And this is kind of good enough for us. We call this the Weierstrass representation, since in the case that the u is 0, it really is the Weierstrass formula for a minimal surface. But what's useful is if you have an immersion into the imaginary quaternions, so an immersion into R3, then you know that the bar of it is its negative. And so applying that to this formula here, you end up looking for things, I mean, we could write this computation out, but bar in the quaternions is order reversing. So it puts the psi on the left and the chi on the right and creates a relationship between the chi and the psi, namely that they're related by a complex multiple. So it ends up being a quite nice condition to see when the map F is into the R3. And so we kind of control R4 using the Kodaira representation, or we control admissible maps into R4 using the Kodaira representation, and admissible maps into R3 using the Weierstrass representation. So that is the... How much time do we have? Maybe we'll come back to this at the end. That's just like a fun play around thing. So that finishes the weak setup of the problem. We've taken the idea of conformal maps and we weakened it to this idea of admissible maps. And instead of working with admissible maps directly, we break them into these parts and work with these potentials and sections. So how should we take the limits of admissible maps then? Well, we should take the limits of either the Kodaira or the Weierstrass representation of the corresponding maps. And so what does the limit of the potential look like? Oh, maybe I should have said this earlier. I think it was written up on the board in the Kodaira representation, but it's very important that the potential ends up being an L2 function. Right, so to control the limit of the potential is to control L2 functions. Okay, so to control the limit, you need to control the limit of the holomorphic line bundles. If you're on a compact Riemann surface, controlling a sequence of holomorphic line bundles is well known, very doable. You reduce this to controlling the limit of the divisors, and then you can find some nice limit because on compact surfaces you can find subsequences where they have to converge. The potential, as I said, is L2, so we consider sequences with bounded L2 norm. Then there's a weakly convergent subsequence. But if you look at the limit of the potential just on itself, it can be doing something that's quite nasty. Namely, it can be, or the square maybe is better to say, can be converging and developing a point measure. So the example to have in your head here is the mollifier, where it comes down to the standard mollifier family. It creates a big spike. It limits in some sense to the delta distribution. Well, in the sense of distributions, it limits to the delta distribution. But its weak L2 limit is 0. So we sort of have this phenomenon where we have this large concentration of energy, but the weak limit is 0. And we have to understand, what does that do to the sections? And it turns out that in the sections where you have this concentration of energy, this large point measure, the sections can develop poles. And maybe the remarkable thing, and I said that 4 pi sort of turns up everywhere, is that the order, or how many orders that pole can develop, is bounded by the concentration of energy divided by 4 pi. It's one of these magic things. So in particular, if you know that the total amount of the, if you have bounded L2, then you can only have some finite amount of poles appearing, right? Because each time you have a 4 pi, you eat up some of that total energy. And so, yeah. So the limits, have to be mirror-morphic in some sense, right? With controlled order. Yeah. So let's go back to the the picture. Where's my thing? Oh no. And so what I've done is I've actually programmed in V as R inverse V R inverse V 0 on Z less than R. So the point is I have a slider here R, which controls the radius where the potential is non-zero, and as I make this radius smaller, I make the strength of the potential larger in such a way that the total measure doesn't change, and so I create a spike like that. And yeah, let's see what happens. Yeah. So what happens is, after maybe doing some Mobius transformations to keep some part bounded and in view here, that spike, that concentration of energy, amounts to nothing, right? The weak limit is 0, and so we just have the 0 potential all over, and that corresponds to a round sphere. So even taking a limit of this crazy thing, in the end we get a round sphere. That's nice. There is maybe one interesting thing, and this is a bit complicated, so I'm going to swap the view for a second to set it up. There are certain special values where you can't make some Mobius transformation to keep it all nice. So now I've put in one of these special values, and the special value is namely to make them touch here, right? To make them tangent here. And so what happens when we decrease the radius? Kind of the same thing. Oops, I lost control of it. You still have this round sphere, you have this round sphere. Whoops. And jump to the end. Oh, that was too much. You have a pinching off of some amount. All right, so in this case, you still have a well-defined limit, but we define our limit in that case to be this part to be pinched off, and you fill it in, yeah. So actually, if you go through the proof, what we do is we control the section on the green part. All right, so on the blue part, we know that we have some concentration of energy, or on what was formerly the blue and orange part, we know we have some concentration of energy. So we just put a disk around that and we do some like local analysis. And then we control the global behavior of the section on the green part where there's no concentration of energy. And because these are V holomorphic functions, they have many of the properties of holomorphic functions, including unique continuation. So when we have the limit on the green part, we can do a unique continuation around the blue part and fill it in, and yeah, that pinches off the part coming from the concentration of energy. And so in this way, we have a limiting process, which is Willmore energy decreasing as well. Okay. Questions while I have the diagram open?
Why does this decrease the Willmore energy?
Because if you pinch, so you're having this energy spike, right? So you have some point measure, but we take the weak L2 limit of the potential. So point measures are not seen, and so they're removed. So this amount of energy that is ending up in the point measure is being taken out. Oh, maybe I also did not say in the setup, the Willmore energy is the square of the L2 potential of the square of the L2 norm of the potential. So yeah, taking the limit. So sorry, controlling the potential is controlling the Willmore energy. This is probably missing. Yes.
You need to use that as a bubble with genus around, right?
Uh,
You have that for pi, and you always got a multiple of that.
Multiple. Yeah, that's right.
2 pi squared, for example.
Yeah.
How do you control the genus preserved?
Because we know the behavior of what happens to the section. We know the behavior of sections when you have a concentration of energy. Namely, they have this pole. They develop this pole.
So basically, that says that the pinching is genus around, or the
Yeah, that's right. Yeah. Let me show you one more example to answer your question about higher energies. Reset that to 4.
The rescaled onto pinch thing should be a Willmore surface.
Yeah, that's right. You should be able to take the other side and also make a surface out of what was pinched off. So to make the computer a bit happier, I've just turned off having the surface. Obviously, it was a surface of rotation, so we're just going to look at the cross section, and you'll see what the picture looks like. And now I have to try to manipulate this slider. So now we have one of the much higher ones. Whoops. Yeah, so you see, even for one of the higher ones, you basically get some sphere with some more sphere parts in here. Yeah, so it does. Yeah, the bubbling off things are never complicated surfaces. Six. Yeah, so this is what I said. It can develop poles, concentration of thing, and in the end we control the limit on a well-behaved part and extend by unique continuation. So this is the part of our strategy where we show how to take limits. This is what I just told you. Yeah, I got a little bit ahead of myself. That limit machinery actually just works for all admissible maps, right? So now we want to apply it to constrained Willmore and the Willmore problem. And so what does Willmore have to do with anything? I've spoiled my own punchline. It's the square of the norm of the potential U, the Weierstrass potential. Yeah, the Weierstrass potential essentially gives you the mean curvature vector. So taking its length gives you the mean curvature squared. For compact, we haven't discussed what the relationship between these two different potentials are, U and V, but there's a nice relation for compact surfaces, namely that the difference in the difference of the squares of their norms tells you the degree of E, essentially. And so when you rearrange that formula, instead of working with U squared or norm U squared, you can work with norm V squared. And when you take this limit, you always pass to a subsequence of constant degree. So if you're looking for extreme points, critical points of the Willmore functional, obviously an integer constant doesn't make any difference when looking for that. So you can equally work with the Kodaira potential or the Weierstrass potential when looking for critical points. So we have this definition of constrained Willmore, means that the derivative should vanish on the tangent space of the set of Kodaira representations. And so we're using Kodaira representations to stand in for our maps. The space of Kodaira representations of this four things. Well, actually, we fixed the line bundle. So the three remaining ones. This is a space where every point is an admissible map. Corresponds to an admissible map. So we look for the Willmore functional on this, and we look for critical points. Because it's the square of the norm and it's L2, well, you have an inner product. So this is really just the inner product of V with itself. And when you want to take a derivative, you get twice the inner product in the derivative direction. So this is to say, we have a very nice interpretation of when you are constrained Willmore, namely when this is 0, and that happens exactly when all tangent directions of the submanifold Kodaira are perpendicular to the potential. And so we start with this, and then we have various pairings and inner products that give geometry on this space, and we manipulate this into a condition. And hopefully I remember the slides, and the condition is on the next page. No, okay, I say a bit more about the space of admissible maps. So, as I said, we fix the line bundle E, and we look at the potential in the two sections. So I didn't say this, but the potential is an L2 function. The sections, they have to be W1P for some P between 1 and 2, some detail. And so in particular, we have three things from three Banach spaces. So the set of triples is itself a Banach space. And what are the conditions? Well, the conditions are exactly that epsilon and phi have to be holomorphic. Right? So they have to be in the 0 set of this function. And so on the space, this Banach space of triples, we're looking for the 0 set of a function. That's exactly what I say here. And that's what this Kodaira space is. Now we apply the implicit function theorem, and we want to show that this is a submanifold. The problem is it's not a submanifold. It has singularities in this space. And so we need to understand where the singularities of the space is, the set. And it turns out that the kernel is non-trivial under only two conditions. Either you have a strongly isothermic surface, which have good understanding and good classifications, or you're a holomorphic surface, that the V is 0, which is also very well understood. And obviously all holomorphic surfaces where V equals 0, well, they have to be minima of, local minima of the formal functional, since it's V squared. So they're clearly okay. We have to do a bit of work to check here. And then at all other points, we have a submanifold, so the notion of looking for the tangent plane is no problem. Yeah, question?
Strongly isothermic?
Yeah. That's definitely something I wish I knew. No. So before I found this condition. So isothermic means that away from umbilic points, you have conformal curvature line coordinates. That's the classic definition. There are some equivalent definitions to this. Right, so the existence of conformal curvature line coordinates can also be encoded in having a quadratic differential, a quadratic holomorphic differential of a certain type. And it is also equivalent to the existence of a dual surface, this Christoffel dual surface. Right? Oh, okay, that's, yeah, Lynn, Emma and I, yeah, exactly. So we have these different notions, and actually having the dual surface is the one that works for here, because we can ask that the dual surface be admissible, right? And then we have the same tools available. So now that's isothermic. The problem is, on each coordinate patch, you take this coordinate patch and you look at what the dual surface is, and usually the dual surface is unique. So you have some sort of way, if you have overlapping patches, then you have dual surfaces which are overlapping. But the problem is that there might be some monodromy in this operation. You glue together these local pieces of dual surface, it might not make a surface. And so strongly isothermic is about that globally your surface, let me say it correctly, the universal cover of your surface has a dual map whose monodromy is only translation. This is... Oh, okay. So imagine you have a circle, and imagine that the dual map was like a piece of a spiral. So as you go around the circle, you glue this piece of spiral together and together and together and together and together and together, and because it's a spiral, it doesn't come back to the same place. It comes back multiplied by some amount, scaled up. Right? So this would be a non-example. You come back and you come back to the beginning on the circle, but in the process that you were following, you didn't come back to the same point. You came to the same point scaled up. Yeah. Right? Another one which would work, or like an analogy that would work, is a ball rolling. Right? The ball rolls around and the point comes back to the top, but the curve you've traced out is now translated along every time you do this. Okay. Yeah, so that's one where you have monodromy, you don't come back to the same place, but you've been translated along as by the process. Yeah. It took us quite some time to understand the difference between isothermic and strongly isothermic. I think you were just saved by this question, because now there's not enough time for me to explain this horrible linear algebra. But we know that the set of Kodaira representations is defined by this equation. You look at its derivative, you break it up into some nice pieces. As I said, there's lots of pairings and inner products around, and so you can calculate the adjoint maps to all these things. And then you do these lovely linear algebra arguments where if something is in the image, if and only if it's in the kernel, the orthogonal complement of the kernel of the adjoint, of course. Right? No, I hate this. I have to think about it every time. But the point is, we want that the V is orthogonal to all tangent directions of V. Right? And so you play around with this and you see in the end that V can only be orthogonal to all tangent directions if it can be written in this form. This is a sort of some form describing the perpendicular direction. Namely that there exist holomorphic sections, K, V bar K holomorphic sections as it turns out, such that when you multiply them together in this form, you get the potential. So this is the condition to be constrained Willmore. And why is that nice? Because you take here, this is the equation that upsilon is V holomorphic, that phi is V holomorphic, that upsilon star is K V bar K holomorphic, and so on. And you of course now substitute in the assumption that V is of this special form, which involves these four sections, and you get this lovely system of PDEs, which fortunately is an elliptic system. And so by some magic, the solutions have to be analytic functions. Okay, it is not so much magic. It's sort of the relation of if you know that V is a product of these sections, then you know, for example, that V is not just L2, that it has actually a little bit better regularity. Right, and so then you have better regularity here, so you know the derivative of upsilon has a bit better regularity. And so you do that for all of those sections, and you put that back into the V is now this product of these four sections which had better regularity than expected. So V has better regularity than expected. You put that back in, and you repeat this cycle, and you pump it, and you pump up the regularity to analyticity. Yeah. So I think this is the last slide. Yeah. So what we did when we developed this technique, all right, we developed this very nice way of weakly representing admissible maps, or representing admissible maps in this data. We proved that we can take limits. We have a very nice characterization of constrained Willmore, right? And then together we have that, there's an easy consequence. Easy consequence is that there's a minimum in every class, because you just take a sequence converging to the infimum. This is clearly bounded. Okay, there's a little bit of work to show it's bounded degree and bounded potential. And so you have that there is a minimum. The minimum is attained in the class, and then you apply what we just saw to see that it's actually an analytic function. So you get existence of constrained Willmore, minimizers in every conformal class. So in the dying minutes of the talk, I want to point out what this has to do with CMC. You can ask in our setup, when does there exist a family of flat connections? So it's very important in integrable systems, or one of the characterizations of integrable systems is that there's some family of flat connections. And you can sort of write down, there's a flat connection coming from the connection with respect to which upsilon is parallel. This is sort of some natural connection in a line bundle. And then you can ask, when does this have a family of flat connections? And the condition is exactly when this happens. And it turns out when B0 is 0, then that's the condition to be constant mean curvature. So V is equal to this. And so there's this very suggestive hierarchy where if V is equal to 0, you have a holomorphic surface. When V is equal to a product, when there exists an upsilon star such that V is equal to this, then you have a CMC surface. When you have upsilon star and phi star such that V obeys this relation, then you have a constant mean curvature surface. And these look like you're just adding more and more terms. So there's perhaps some natural hierarchy of surfaces of which holomorphic is the 0th, CMC is the first, constrained Willmore is the second, and who knows what is beyond that. Yeah, so that is the end of my talk. Thank you for listening.
Thank you.
Yeah, so as I said, this is joint work with Martin Schmidt. Martin thinks that that there might be some interesting geometric things here. Which is possible to investigate. These conditions get easier as you go up, right? Because there are more sections, more ways that this could be possible. I would be interested to know if you take some sort of closure or some sort of limit of having as many as you like, can you approximate, is this class large enough that's filling up the space of admissible maps? Is every admissible map is this some sort of finite type hierarchy? And then everything is a limit of finite type things. But we don't know how to investigate either question.
And also the word hierarchy is
okay, yeah.
Right, like what is the system which this is the hierarchy?
Yeah. Well, that was asked last week, and then arguments broke out, and yeah.
So is it weak formulations?
Mm-hmm.
And in all this process, you are preserving actually, or you're fixing the Riemann surface structure.
Yeah, that's right.
Now, is this clear that when you have this weak formulation, that the resulting map is really something that will preserve your Riemann surface structure? Can your Riemann surface structure still like diverge or whatever?
Yeah, so that the Riemann surface is just fixed throughout. At no point do we consider changing the Riemann surface.
Yeah, but is a weak conformal map thing enough to avoid pinching? Like pinching off its neck, for example. I mean, well, if you have
Oh, pinching off. Yeah, no, that doesn't happen. You just pinch off discs. You only ever pinching off discs and filling them in with dots again.
How does that argument work?
Huh?
How does that argument work? Why pinch off discs?
So you look at L2 potentials and how energy can concentrate in them. And then if it's concentrating, we know we have a finite number of points of concentration because the total energy is finite. And so you take some disk around each point. Then you take that disk and you embed it in P1 and you use Mobius transformations to blow it up and deconcentrate the energy. Repeat if necessary. If when you blow up the energy again, there are still converging point measures and so on. And so we control it by taking this disk, putting it into P1, doing Mobius conformal transformations, and then controlling what the limit is, and then blowing everything down again. Yeah, so there's no potential for it to do anything else. It's just always disks. Yeah.
Okay.
Yep.
Actually, I have one more question. I suppose you want to do higher dimensional Willmore surface in some higher dimensional ambient space.
Mm-hmm.
There's some kind of similar formulation in terms of representing using
Yeah.
analog of this Kodaira and Weierstrass.
There is. So we didn't come up with this idea of this Kodaira map, this one.
Kodaira actually, that works for CP. Like, that's all.
Hmm?
Sorry, go on.
Yeah, so here we have a map into H, and so we have two sections, right? So we actually have a map into HP1. So if you take more sections, then you get a map into HP whatever.
So you do some
Yeah.
bigger
Yeah, more sections equals, yeah. The problem is that then you're no longer in the land of line bundles or holomorphic quaternionic line bundles. You're in the situation of higher rank line bundles. And in particular, then your potential is no longer described by a quaternionic function, it's described by some quaternionic matrix. And this is much more complicated because there's a natural metric on, essentially there's a natural inner product even on the space of potentials for line bundles. But there's not a natural inner product on the space of potentials when you go to the higher rank case. You have to make some choices. And your choices are not as good as the natural one that you can do in rank 1. Yeah, so possibly this could be done, but it would change the analysis a fair bit, I think.